waveform agents is an AI agent which we've designed to autonomously perform the end-to-end waveform debugging task. And so we're really excited about what we've been working on here. And so we at ChipAgents, we know that waveform debugging is particularly challenging. There's several reasons for this challenge as well. So the most obvious reason why waveforms are notoriously difficult to debug is just because they're so large, right? You usually see tens, hundreds of gigabytes of data, and in large systems, it's not uncommon to see even terabytes of just raw data. And on top of this, usually the bug that you're trying to solve, or the issue that is in the waveform, is usually manifesting itself in some small temporal range in relation to the overall size of the waveform itself. And so what this dynamic causes is this sort of needle and haystack problem. You have an unimaginable amount of hay, and some needle that you're trying to pick out from that haystack. And to further go down this analogy, it's one problem to actually find the needle in the haystack. But there's an equally important problem that comes after that, and that's actually how do we actually pull the needle out of that haystack? And so the same is for waveform debugging. You can do all the localization you want, find the issue in the waveform, maybe in the design and test bench files. But ultimately, at the end of the day, what you need to do is provide a fix to solve that bug. And so that goes into the problem of pulling out the needle, fixing the bug. That's also challenging because what this requires is some intimate knowledge of the different signals, their relationships to each other, and how they interact with each other, and also their appearance in the actual design and test bench files. You need to know how they're actually interconnected with each other. You also need to know how to interpret the different signals, and so on. And so this just ends up being a generally difficult problem, very time-consuming, lots to come over. And so we can start by talking about how engineers are debugging waveforms today. One really good system out there that people use is waveform viewing software. And this makes a lot of sense because waveforms are an inherently visual medium, right? You have to group the signals together with your eyes. You have to watch them toggle at certain times, and you might be looking for some certain protocols, for example, in the waveform. And so we still see the same problem as before, though, where waveforms are just so big. It's still a lot of data that you have to actually comb over and look through visually. And it's just infeasible to have to do that, basically. Along with these waveform viewing softwares, it usually comes with this sort of signal tracing features where you can actually see which signals are influencing others. But also, this process is pretty much managed by the engineer who's conducting the waveform debugging. They have to guide that signal tracing process. Moreover, even if you do localize the issue in the waveform, again, that problem still comes back where you have to actually fix the problem. You find it in the waveform, you have to make the fix. The next thing that people often use is some sort of anomaly detection. So these are using some pattern recognition based off of traditional machine learning techniques, for example. And there's a few issues with this. The first is that these algorithms don't really consider how to interpret the different signals and how they're actually used in the design and test bench. All they're looking for is certain patterns and how they toggle and their values in the waveform. They don't really know how they're necessarily connected within the design and test bench. The other thing, too, is that these models are usually trained on some signal database where there are maybe some anomalies that are existing. And so what this means is that ultimately it's trained on these types of anomalies. But what happens is that let's say there's some new or novel anomaly that's in the waveform. These systems will not be able to catch that because it's not necessarily trained on it. So it's not very flexible to unseen use cases, basically. And finally, we have formal tools. Again, these are a very powerful tool. They can help you find some counterexamples in the waveform, for example. But like with most things with formal tools, they don't scale to larger systems. As soon as you get large enough, it collapses on itself. And even if the formal tool was able to work on your design and you get some counterexample, you still have to rummage through that waveform, find exactly where the error begins its propagation, and drive the effort to fix it. OK, and so now we can get into a discussion about LLMs and AI agents. So you might be thinking to yourself, OK, what about LLMs? Can we leverage large language models in order to solve these problems? And when I say large language model, I'm talking about your standard, tokens in, tokens out, next token predictor. And I argue for this presentation that no, actually you cannot waveform debug with just standard LLMs alone. You actually have to use AI agents. And so what are AI agents? I think a great definition is AI agents are large language models which can actually take action in the environment that they are operating in. And so I actually have a picture up here in the top right of me putting a waveform through ChatGPT. And it's sort of funny because at the top there you can see, or maybe you can't see because it's kind of small, but it says the file is too large. Again, like we said, this is the central problem of waveform, so it's sort of funny. Let's suppose that the waveform was small enough for ChatGPT, for example, to process. It's still not going to do a very good job of actually processing it. And this is because large language models are just trained on natural language alone. And waveform formats are somewhat readable, but they're not very human readable. And also you have other formats of waveforms that are in some proprietary formats, for example, that are definitely not human readable without some domain-specific tools. And so I'd like to go over some differences between LLMs and AI agents, just to outline the differences more clearly. The first is that LLMs, they're next token predictors. So this means if in one token, some error is introduced in the generation, that error is going to ultimately propagate to the next tokens that are being predicted from that point. And this causes issues like hallucination, for example. With the AI agents, we don't actually see this problem because the AI agents are able to produce their own verified feedback by interacting with the environment that they operate in. So this means that if at any points the AI agent starts to maybe veer with some error propagation, it'll generate that verified feedback and get itself back on the right track. And we see that this ultimately improves performance. As a consequence of this, LLMs are mainly reactive. So this means that it's mainly driven by the user who is actually using the LLM. You give it a prompt, it'll give you something back, but ultimately it's up to the user to take the next step of action in order to fulfill the goal that they are trying to achieve. AI agents, on the other hand, they are self-directed. So this really means that the user, when they're using an AI agent, can give it some sort of goal, overarching goal, and the AI agent will take action and specifically find the path on its way to actually solve that goal. It's not going to wait on the user to do anything for it. And lastly, LLMs don't necessarily have intelligent context selection. Now, with humans in the loop, obviously that sort of is intelligent, right? You're having the user select the intelligent context. But oftentimes in very, very large projects, finding the relevant context actually is a hard problem in and of itself. And so we can offload that to the AI agents, which can intelligently decide its context and do that sort of exploration on these very, very large project bases, very, very, very large waveforms, for example. And so there's kind of this interesting idea about how domain-specific problems actually require domain-specific tools and implementations. And here at ChipAgents, that is exactly what we are doing with our waveform agent. So in short, standard LLMs have no hope to understand waveforms, but AI agents can. And specifically, the implementation here at ChipAgents is designed specifically for this. So now I'll go over a high-level overview of what waveform agent is. This is our new feature at ChipAgents. And as I mentioned before, you give it a goal, and it will go ahead and do that goal. And so here's an example use case of waveform agent, actually. You can say you have a failing test case. Well, you can simply say, why is this test case failing? And what will happen is that waveform agent is going to go in the background, and it's going to do all this manual signal tracing, all this manual cross-referencing between different signals that it sees in the waveform and how they connect with each other and how they appear in the design and test bench. And it's going to do this full end-to-end debugging task. And the really important thing here is that it's understanding how the signals relate to each other, and it's not stopping at just localization. So once it actually spots the issue in the waveform, it'll go ahead and actually solve that issue. And so we get three kind of qualities here. The first is that it's scalable, because of course, like I mentioned, it's doing that intelligent context selection on its own. So it's able to sort of parse through this, large amounts of information, whereas an LLM is definitely restricted by just its strict, context limit. It's flexible because it works on unseen use cases because it's using the intimate knowledge that it gains throughout its exploration to actually understand how the signal should behave, especially if there's a specification involved. And finally, it's automatic. As I mentioned before, you give it the goal, it'll do the exploration all on its own. Get some water. OK. And so now I'm going to spend some time doing a live waveform agent demo. OK. So let me make this bigger. So what I have here opened up is AES module. And actually, one of the test cases is failing. So make clean. I am in the wrong directory. OK. Let me make sure I'm in the right directory here. Wonderful. OK, so now I'll showcase that there's a failing test case in here. So make clean, make all right, and then I'll finally run the simulation, so make sim. And so what we see here from the output, right about here, is that the first test case is passing, but the second one is actually failing. And so, you know, in the case of the AES module, there's a lot going on here. So what we'll say to a chip agents is we'll say, my first test is failing, passing rather, but my second is failing. Why? Use test bench VCD. And so test bench VCD was the waveform that was generated by running this simulation. And so now it's going to run in the background, and it's going to do all those qualities that I just talked about before, that different signal tracing, the different cross-referencing with the different files in the design, and you know, all these different exploration, intelligently selecting that context. And so while that's running, I have another conversation thread that I spun up for the sake of the demo. So let me pull up this other thread. Whoops, stream. And so as we've seen, I'll go back to the thread that I just started earlier once it's finished. But we've already seen one use case, which is the use of waveform agent for debugging and actually making the fix. But waveform agent is also good at understanding waveforms in general. You can ask it general queries, general questions. You can also ask it to check certain invariants that you want to be true in the waveform as well. So here's an example of a thread that I started. And I asked it, I have this chip.vcd, which is for a network on chip. And I said, looking at the project in the chip.vcd, I want to understand what chip interface NOC2 valid does. Can you describe how it interacts with other signals? And so very similarly to what you saw before, it does all this exploration, and it does two things. It'll generate some sort of explanation as a response to your query, and it's also going to pick out some specific timestamps that are relevant to that query. And so here, you can see it does a really good job of saying, you know, it's part of this bidirectional NOC2 interface, and it's saying there's, you know, two kind of like multi-directional here where you have going from the interface to the chip and then the chip to the interface. And there's this, there's a certain protocol that it picks out as well. And so you can see the signal operates in a well-behaved handshaking protocol. The transactions are multi-cycle with data changing each cycle. And it's primarily being used for chip to interface. So it's actually not seeing a lot of data being passed from interface to chip in this waveform. And then here you can see it actually gives a list of the supporting timestamps. And these are actual timestamps that you can now you know, plug into your waveform viewer, navigate to these timestamps, and see exactly what you want to look at. And to kind of further drive home this point, here's another one where I'm sort of asking for an invariant in the waveform. I'm asking for you know, how many cycles there's like different bursts with the data from the, I think, interface, from the chip to the interface, in bursts of either 1, 2, 3, or 4. And this particular waveform has bursts of 3. And so sometimes there are bursts of 4. And instead of manually combing through that entire waveform, because it's quite big, this one, for example, is 1.17. Obviously, waveforms can be bigger, but when you're viewing this waveform in the viewer, it's, you know, hard to find all these different portions in there that you might be looking for. And so here we can see ChipAgents easily picks out that there's actually no burst of 1 or 2, and that they're only constrained to bursts of 3 and 4. And in addition to this, it actually helpfully gives us timestamps where the 4-cycle instances happen. And so this is really great if you're trying to actually do the localization in the first place, and if there was some issue that was relevant at that timestamp, you can then go ahead and ask it to fix whatever issue was happening. And it'll go through and look at the files and make the change. So this is all really great. And then, of course, I give it thanks because now I spent less time waveform debugging. OK? And so now if we come back here, this was the AES module that was failing. And again, I want to emphasize that there's a lot of weird, tricky math that is happening in this AES module. I'm definitely no AES expert, but there's like Galois multiplication and like this mixed columns, I think. Yeah, so there's like some strange multiplication happening here. And so what you see here is if it's done exactly what you've seen before. And it actually picks out that it fails to return to the idle state. So this particular bug is interesting because the first test case passes, but the second one fails. And so it's just kind of a weird thing. You can look at the waveform and try to figure it out, because you would expect for something as complicated as AS, if it's passing this one case, it should be working, I guess. But in this case, there's a state transition issue. And ChipAgents successfully picks it out. So it says the AES state machine fails to return to the idle state, stage 0, after completing an encryption. In the code, the state machine sets done to 1, but then it transitions to stage 1 when it actually should transition to stage 0. And so, of course, I could have gone through that and figured it out myself, but instead I've let ChipAgents actually save me all the time of looking through the waveform, looking through the files, and actually fixing the bug. And so what I'll do is I'll say, make the change for me. And now it's going to work from all the information that it's synthesized. It's going to reread the file just to make sure it knows what it's working with here. And now it's going to actually propose a fix. And so what I'll do is I'll accept it. I'll go back to the simulation. I'll make clean, remake it, and I'll make sim. And now we see all the test cases are passing. OK? And so that's all I have to show for the waveform agent demo. We'll go back to the slides. OK, and now some really exciting and interesting results here is we've been benchmarking waveform agents with an internal benchmark that we have at ChipAgents. And we see that against some state-of-the-art LLM, waveform agents is performing much better. And on the x-axis here, you can see that we have a reasoning budget. And then the y-axis is obviously the performance on this task. The task at hand is specifically waveform debugging. So given some bug and some design and the waveform, how well and how often can you actually solve that bug? And so this benchmark we're designing to be a very realistic setting, where a lot of other benchmarks might be a little saturated, might be too easy. What we're really striving here with this benchmark is to be realistic so that people can have confidence in what they're actually using. And another interesting thing that you can see here is that as you increase this reasoning budget, you actually kind of see it tail off for the state-of-the-art LLM. So it's actually not getting any better with each increase of the reasoning budget. Whereas with waveform agents, you can see it's constantly increasing, all the way up to even 53%. And so it's really exciting to see these numbers, especially on such a benchmark that is supposed to be realistic. And one of our future plans is to actually open source this benchmark. And so we're excited and looking forward to that as well. OK, and finally, some use cases for waveform agents that we anticipate being really important for people moving forward is this idea that you can run your nightly regressions, for example. And let's say you have some bugs that appear in that. Well, ChipAgents, waveform agents, can actually be your first line of defense and perform that automatic bug triaging for you. And so really, we imagine ChipAgents being attached to the end of this pipeline and being able to automatically resolve those issues that might come up. And so this is all I have to show today. Be happy to take questions.
If you have a question, there are 2 aisle mics. If you could just step up to the mic if you have a question. Thank you.
Great talk. Thanks. So my question is, as we analyze the waveform, typically we have the performance issue, right? Okay, here. Okay. So for your waveform agent, do you have any kind of capacity issue? How big the waveform you can analyze? And what is the performance, runtime performance to analyze that waveform?
Sure, yeah. So the question was if there is any capacity on the waveforms that it can handle, and what is the time complexity of it. Okay, so there really is not an exact limit to the size of waveforms it can take. And this is, again, because of what I mentioned earlier about there being some intelligent context selection. So this agent isn't merely just taking in the entire waveform. Imagine it was. That would be completely infeasible, right? And so there's this sort of intelligent context selection that's happening there. In terms of the overall complexity that it takes for the waveform, this does depend on the size, the overall size of the waveform. But ultimately, this depends on the tool chain specifically that you're using and what kinds of time complexities that they have for their own parsing. Because waveform agents is attaching itself to the environment itself and using those tools in the environment. Does that help answer the question? Okay.
Thanks.
Great.
Can you hear me?
Yeah. Yes.
So what is the reasoning budget that you mentioned in the graph?
The reasoning budget?
Yeah, and how is it calculated?
Yeah, so you can just think of that as the amount of compute that is going into the solution.
Okay. What's a straightforward way of calculating that?
I'm sorry, I couldn't hear that.
What's a straightforward way of calculating the amount of compute? How do you get that?
I see, yes. So again, LLMs, right, are like next token predictors, and the driving engine of AI agents is that LLM. And so ultimately, what we're talking about with the reasoning budget is how many tokens we're allowing it to actually generate, and like that sort of thing. So how much compute you're doing with the token generation.
Okay, so that brings me to the next question. But how big an LLM are you using? What sort of LLM are you using underneath your tool?
So I can't answer that question exactly, but I can tell you that we use a lot of different, bespoke methods on our models and the different orchestration that we handle with our agents. So I can't really touch too deeply on that, but okay. I hope that answers your question.
Okay.
I had a question on, I think it was your previous slide when you were comparing it against the state-of-the-art LLMs.
Yes.
Can you talk a little bit about, which LLMs you consider as the state-of-the-art?
Sure. Yeah. So models like Gemini, OpenAI's ChatGPT, for example, the O3, for example, and also Claude.
Thank you.
Yes.
So the next question is about the quality of the generation or the workflow. So it's very easy to look at the screen and see, wow, it does something. But coming back, how do you systematically evaluate the result of a complex workflow? And do you have any time estimate, whether it will take a day or a minute, or you have no idea how long it will take? So 2 questions. One is how to evaluate the quality of the result systematically, not just by visually browsing. The second is about the time budget or computing budget. Okay, yeah, so the first question is how do we actually verify systematically? And so with this current benchmark that we have, we are actually testing the performance by running some simulation in the background. And so again, the task is given a bug, and maybe a waveform. Can we solve that issue? And the way that we measure that is if it actually reverts the bug and solves the issue. And by running the simulation, exactly. Does that help? And then your second question was time. Okay, so when you're doing long overarching tasks, the time for it. Yeah, that's a good question. I think I don't really have a good time estimate for the particular tasks in the benchmark, for example. But in general,
I think it kind of has to do with the size of the waveform as well, because you can imagine if you have a larger waveform, it's going to be a longer overarching task. And so I think that kind of goes back to my original answer to the waveform problem, where it does scale with the size of the waveform ultimately. And so I guess that's a good way of determining the overall time of the workflow. Yes.
Hi. Yeah, thanks for the talk. So first part of my question is, how big a design have you tested this on? Is it more for a block level design, or have you tried anything on as big as a SoC?
Yeah, so to give you reference, the benchmark is using the largest open source projects that we could find.
The second part is, you showed that it is consuming a VCDT right now. So do you also support all various different formats for waveforms?
Of different formats of waveforms?
Yes.
Yes.
Okay, the FSDBs, the WSFs, everything.
Yes, because at the end of the day, we ultimately attach to your environment, right? And so if your environment requires these tools, we require you to hook it up with ours, basically.
Okay, yeah, thanks.
Yes.
Yes, I want to know about the inputs that are needed for your tool. So I noticed in your AES example that you mentioned that you have passing and failing tests. Is this information that you have passing test important? Does it mean that that your tool compares a passing and failing test? And my second question is whether you give it a specification as a reference.
Mm-hmm.
So how does your tool know about the state machine? Does it get information from the specification or RTL microarchitecture? In general, I want to understand how does your tool know where to look for the reference?
Okay, yeah, good question. So the first question is, does it need to know information about the test case failing? And with all agents or LLMs, it's always better if you're providing more context than none. But it is possible to just say, look at the waveform, do you see anything weird, right? And it will sometimes go through, and it is able to actually pick out some anomalies or things that it thinks are odd, and it will give the user some suggestions of, this doesn't look quite right. And so that sort of answers that question. The second part is how does it know about the state machine, for example? In this particular demo, it actually was able to infer just by looking at the files. And this is what I meant earlier in the presentation by being able to actually cross-reference the waveform with the design and test bench, right? Because it's looking at these signals in the waveform, and it understands that, oh, wait, this signal is a part of a state machine. Okay, there must be a state machine in the design. Let me check it out. And so actually in one of the files, it does see where it's defined, and it's able to pick out that the state transition is incorrect. And if you have a specification, again, like I mentioned earlier, the more information that you actually have on your query or prompt, the better. And so, specification definitely helps in that case as well.
Thank you.
Yeah.
Hi. My question is regarding, do you have a plan to extend it to gate level simulations also? Or
I'm sorry, what was that?
You have a plan to extend it to gate level simulations also?
Gate level simulations.
The netlist level simulations.
Not at this time. I'm not sure, but yeah, it's something we can think about. Yeah.
Okay, thank you.
Hi there. I have a quick question about the input files needed for the tool to understand. Sometimes we have a mix of clear text RTL, and sometimes we have encrypted RTL, and also we will have gate level netlist from ASIC gate or FPGA gate, and also for ARM CPU, we sometimes has DSM model. So does your tool support a mix of all these inputs on debugging, or is solely can understand clear text Verilog RTL? Yeah.
So yeah, yes, it's able to understand like your entire project, right? And so if you have files that are relating to different kinds of things, then yes, it's able to look through that and infer how each part is connected.
So even encrypted RTL, because usually it's
I'm sorry, I can't hear you.
Sorry. For encrypted RTL, right? Because even human can quite understand, so the tool can still understand how it works.
That's
right?
right.
Okay.
Yes.
Thank you.
Just a quick question. So you mentioned a while ago that it's getting the input based on your this chip agent is based on the RTL the test bench and even the specifications. So if there's a bug, which does it know that it needs to look into the specification first as a golden reference before looking into the RTL codes or the test bench? Or
yeah. So generally, I can't exactly say with definitive knowledge about what it actually does determine to be its truth. But in your prompt, for example, if you do know that you have like some source of truth, you can identify that in your prompt, for example. But if not, and if it sees discrepancies, these things are really good at digesting a large amount of information, and so it definitely is able to see discrepancies between these things and make some sort of judgment on what it thinks is actually the ground, what should be the ground truth, or something that looks off. Does that make sense?
Yeah, I guess so. But it's now it's just a little bit of follow-up. It's just that if there's inconsistency between the design, the test bench, and the specification, and it doesn't know that it needs to follow the specification first, then I mean, in general, the specification is like is supposed to be a good signal for like moving forward with the design, right? And so, but ultimately, like I said too, it is determined by what the user actually prompts it with as well. Okay, so I can say that just follow specifications and it should probably.
Yeah, and if you don't, like I said, it's good. It is good at picking out discrepancies, and I can imagine that it will actually tell you, hey, there's something that looks off here, and it'll tell you, what sort of judgment it's making throughout the decision-making process.
Oh, okay.
Yeah.
I'm kind of new to the field, so hopefully it's not too stupid a question. But so the underlying knowledge is coming from the LLM, right? Do you have to train it to feed a lot of feedbacks and train it at how to find bugs or how to get information?
So I can't go really deep into that question. So I mean, you kind of get the same answer that the other person got before, where we use a lot of different bespoke methods and different kinds of ways that we orchestrate the agent itself. But yes, there is a portion of the knowledge that is underlying from the LLM, and the knowledge comes from the different parts that we inject with the model with how we, like I said, the bespoke methods that we use on the models and things like that. Yes.
Question, can the tool identify power bugs like wasted clock cycles or come up with improvements for power?
Yes, that's actually right. Yes, in the benchmark, we actually have problems that are like that, where there is some bug which is causing some slowdown in the cycles. And yes, so that's a part of the actual benchmark that we have.
Just one more thing. Will it know if I did will it be able to identify if there is an actual bug in the design or I just made a stupid mistake in test bench generation of stimulus?
Right, yeah, so you're talking about if the bug is actually in the test bench, right?
Yes.
Yeah, so in that case, the agent can still, that's why I said cross-references is both the design and test bench, because of course the bug can be in the test bench, right? And so it's going to look at that and it's going to make that decision as well. So it's able to fix bugs that are in the test bench as well.
So it seems like that we'll have to train this model on our design, our spec, specification, and our test bench, right, every time. So is this a single time event, or if I'm running a regression with 1,000 tests, say, will it go parse the log files every time, and is there a requirement from the DV person to actually encode the failures in certain signatures so that it can actually parse it easily and kind of go and triage it itself? So that's one. And the second part is the training done every time that it is kind of triggering and going and debugging each failure signature.
Okay, so the first question you're asking, do you have to actually give it the log files each time for like the different debugging processes? And the answer is no. And again, because like I mentioned before, you do the intelligent context selection. So it's able to actually pull that information out on its own. If it sees a log file and it thinks it's interesting and important to the overall bug, it'll pull that in. So no, you don't necessarily have to.
the second part you're asking is, can you repeat the second part again?
So the second part is the training part happening each time that it's kind of going and debugging one particular signature?
Is the training part happening every time?
Right. Will it go and parse the specification again and the relevant part of the code again and the specification again? Or is it just a one-time process per project?
So actually, I mean, with LLMs, you have this pre-training process, right? And so all the training happens there. And so any additional knowledge that it needs, it's going to find throughout the like the project itself. So there is no additional training that needs to happen. It's going to understand and figure it out on its own while it traverses the project.
Okay, so if I'm doing a regression for one single project, this is already a pre-trained model which has the knowledge of the code base, of the specifications, everything. And
I'm sorry, I couldn't hear very well.
Sorry, if I'm running a regression for one particular project, right, which has 1,000 tests, for instance, so it's gonna already have a pre-trained model which has the knowledge of the design and the code and the test bench and everything. And it's just gonna go and actually look at the signatures and reference that code base, or database rather. And
so there was no training that was necessary for the regression. It's just going to take the regression as it is and solve the bugs that come up through it just as it is. So.
Okay. And does the errors have to be in some certain syntax or some particular standard? I mean, it can come out of any of the different submodule test benches as well, right?
Yes, it can be any bug. It doesn't need to be some specific type of bug, for example, or anything like that. It can be very generalized, actually.
Assertions, functional failures, anything it can pose. Okay, yeah, thanks.
Hi, Zackary. I'm glad we're still taking questions. At the beginning of your slides, you showed a snapshot of ChatGPT saying that the inputted, raw BCD file was over the context link. What kind of strategies does ChipAgents use to get over?
I'm sorry, I can't hear you very well.
Oh, sorry.
Yeah, you're good.
At the beginning of your slide, you showed a snapshot of ChatGPT, and it was saying that the inputted, likely raw VCD was over the context length. What kind of strategies does ChipAgents use to make sure that these inputted waveforms don't go over context length, and you can actually, have them in your prompt?
Sure. Yeah. So I mean, again, I think this goes into what I've been saying throughout the presentation, which is the fact that it does the intelligent context selection. It's doing the traversals and exploration on its own, and it's able to actually choose what it's looking at, for example. So this means it's not digesting the entire waveform. It's picking out where to look, deciding whether it's relevant, for example, and so on.
Thank you for all the questions. I'm sorry we're going to have to cut them over there. We have to move on to the next session. If you have any questions for Zach, I'm sure he will be happy to answer questions to the side of the stage. Thank you very much.